created. A force that is applied to an object at the same frequency as the object's natural frequency will amplify the vibrations of the object. Frequency can be caused by strong winds blowing against the bridge, creating regions of high and low pressure above and below the bridge. This produces very strong oscillations or waves on the bridge, causing it to break or completely collapse. The wind that can break a bridge is around 40 miles per hour. Most earthquakes have a frequency of around 20 hertz. This is how we knew what number of frequency to test out the bridge.
I had some background knowledge on how to build a bridge from my 8th grade year science class. We did a final project somewhat similar to the one we are doing now, except that one was more of how much weight it can hold. I remembered that one of the most stable structures, although it doesn't look like it, is a triangle. Some of the strongest bridges have complex designs of triangles. While designing the bridge, I knew I wanted the bridge itself to be entirely made out of triangles. For the road, we connected 9 triangles together to make a rectangular shape. We did this twice, and once both were finished, we glued them together to make the road stronger. Next, we laid the cement and placed popsicle sticks over the road to give it a smoother surface. For the walls of the bridge, we repeated the rectangular shape of the triangles and placed one on either side. For lateral bracing, we placed larger popsicle sticks on top of the bridge to form a truss. This helps to keep the walls of the bridge from swaying too much once a frequency is applied to it. A bridge is only as strong as its base is. However, we created a box out of popsicle sticks and placed 2 additional popsicle sticks in the center as an X to create 2 smaller triangles. We connected the base of the triangle with popsicle sticks to create a smaller triangle. In my research, I found the best way to build a strong bridge is to have a strong design. In that design, there should be 3 things: some type of lateral bracing, triangles, and an underside support.
Resonance is the reinforcement or prolongation of sound by reflection from a surface or by the vibration of a neighboring object. It is clear that bridges and buildings have fallen down due to the effects of resonance, or to be more precise, mechanical resonance. One of the most famous examples of a resonance disaster is the 1940 Tacoma Narrows Bridge collapse in Washington, USA, which came about not simply as a result of mechanical resonance, but also aeroelastic flutter, which is a process that occurs when complex varying oscillations are caused by passing winds. In relation to the bridge we constructed, we tested the frequency of the bridge in order to see which frequency was closest to the resonant frequency of the bridge. From our experiment, we came to the conclusion that 10.800 Hz is closest to the resonant frequency because that is the frequency where the bridge shook more. Though it is stationary, it appeared as if it could possibly collapse or pieces of the bridge could fall at that specific frequency. However, due to the stability of the bridge and its construction, resonance did not affect the bridge. We tested 8 different frequencies ranging from 8 Hz to 30 Hz, and we noticed anything closer to the resonant frequency would cause the bridge to shake more, whereas frequencies farther from 10.800 Hz barely shook. All in all, when building a bridge, architects and engineers must keep several concepts of physics in mind, especially resonance, because if the bridge is not constructed properly, it can collapse due to resonance, just like the Tacoma Narrows Bridge. All right, this is 10 Hertz. Jennifer's putting the car in.
That's weird. The car's like not moving at all.
I'm going to be talking about how forces and the law of motion apply to our project. Every object in the state of uniform motion tends to remain in the state of motion unless an external force is applied to it. The relationship between an object's mass, its acceleration, and the applied force. Every action there is an equal and opposite reaction. When testing our bridge's reaction to different frequencies, we placed a small toy car in the center of the bridge. When we set a high frequency, the car began to shake and move with that bridge. When set at a low frequency, the bridge shook less, and so did the car placed on it. Our research shows that high frequency causes the car to move rather than the low frequency. A force is a push or pull upon an object resulting from the object's internal interaction with another object. Using the digital function generator, we placed two ends of the bridge on the machine and applied different levels of forces to cause the bridge to shake. The car was a force on the bridge, but was not a big contributor to the project because it lacked an ideal mass necessary to affect the bridge.